Welcome, everybody. I am pleased to welcome you to our second webinar of the 2026 webinar series. My name is Dan Stanke, and I'm an assistant teaching professor in the Water and Wastewater Technology program at TRU. Before we would begin, I would like to acknowledge that Thompson Rivers University campuses are located on the traditional lands of the Tecumseh and the Tahoot within Secwepemcúlecw, the traditional and unceded territory of the Secwepemc. Thompson Rivers University and its partners host an annual free webinar series and courses designed to provide the technical information, resources, and tools to all small water system owners and operators, including Indigenous small water systems. These webinars, courses, and the website cover topics such as treatment, regulation, operations, maintenance, and water quality monitoring. The Online Help Center is committed to assisting small water systems across BC in implementing a multi-barrier approach to drinking water, ensuring safe, potable drinking water for their communities in compliance with government regulations. Our free webinars are scheduled every 2 months. If you are an EOCP certified operator, each webinar will count as zero point 0.1 CEU towards your certification. Upon completion today, participants will receive a certificate which can be submitted to EOCP. An important note here is we wanted to let you know that we're going to be launching the Math for Small Water Systems course about mid-April on this website. So please keep an eye out for it. It's going to be a good course. Now getting into today's webinar. It's going to be a 1-hour presentation followed by a 30-minute Q&A session. If questions arise during the presentation, please note them in the chat section and we'll address them afterward. Our topic today is unidirectional flushing. This webinar will provide an overview of unidirectional flushing, UDF, a proactive maintenance technique used to improve water quality and system performance in the distribution system. Through a blend of theory and practical application, this presentation will cover the purpose, benefits, and methodology of UDF, along with tools and templates for applying these concepts. It's my pleasure today to welcome our presenter, Scott Jameson. Scott holds level 4 certifications in water treatment, water distribution, and wastewater treatment, and he runs the company Jameson Water Services, which can be found online at jamesonwater.com, where they provide hands-on training and consulting services in the operations and maintenance of water and wastewater systems. Please take it away, Scott.
All right. Thank you for the great intro there, Dan, and thank you everyone for logging in for this seminar. This one, for many of you who may have attended the one that happened almost exactly a year ago that I did on flushing programs. This is a continuation of the themes we talked about last year and trying to move that flushing program into a unidirectional flushing program or a UDF there. So as we mentioned, we'll try to go over the steps on how you can do that process. So why are we going to do this first? Well, once again, this is considered to be the best maintenance procedure that we can do to maintain water quality in a distribution system. So by doing a thorough flush of the system, we help ensure that we've got that clean, fresh water throughout the system. And then we're also trying to do the best job we can at removing any debris or biofilms that may have built up inside of the distribution system piping. Now, also with doing a unidirectional flushing program, it really also helps our operators find valves in their system and have a better understanding on how the water flows around their system. And hopefully we also get those other benefits like maintaining those chlorine residuals throughout our system. And hopefully we also reduce the amount of times anyone in our water system is calling in with a taste and odor complaint. Now, if we look at why we want to do a UDF, we can look inside of the pipe here and try to see what type of a flow pattern is generally created inside of the pipe. And what you see of the diagram at the very top, that is kind of the regular use of your system. So people having showers, flushing their toilets, what you'll get is you'll get flow just moving down the very center line of the pipe. And the water that's on the edges doesn't move very much. And therefore, that becomes areas then that the debris can settle out and biofilms can build up on the inside of the pipe. Now maybe we can move down to the middle point there where we increase the velocity or the speed of the water moving through the pipe a little bit. But what we're really trying to do, especially with a UDF program, is we're trying to maximize the velocity or the speed of the water moving through the pipe and therefore maximize the amount of turbulence that we are creating within that pipe. And we want to get the water rushing up against the edges or the ends of the sides of the pipe and hopefully grabbing any debris that might build up there and dragging that along and down the line and maybe tearing off any biofilm or slime that is growing on the sides of the pipe. So, with a UDF program, that's really what we're targeting. We're targeting this idea of trying to maximize the velocity we can achieve within the pipe while we're doing our flushing. So, worry about this one, right? And it's kind of going back to the previous course, just this idea that, hey, our flushing can go in various different forms. The one here we're focusing on is the unidirectional flushing one. So, and with that one now, for a unidirectional, this is where we're going to put in some procedures and steps into our flushing program to make it more efficient. And the overall idea is that we're going to do the flushing in a very planned way, make sure that the water is only going in one direction only. And by doing that, we're able to maximize that flow velocity, right? And we get the best scouring that we can possibly get with our flushing program. So we're going to do a lot of the same planning steps as we're going to do for a regular flushing program. We're just going to add in a few little items on there. The main one being that we're going to have to manipulate valves in our system to ensure that the water is flowing in one direction only. And we know exactly, hey, well, water's flowing from here where I have clean water. It's going down this street, taking a turn, going over here, and it is scouring these pipes only. And I don't have water going around in other different directions while I'm doing this program. Now, I've mentioned that we're trying to maximize velocities numerous times so far. The AWWA, through research, what they have come up with is that if you want to remove sediment that has fallen in the bottom of the pipe, you need to achieve at least 3 feet per second or 0.91 meters per second of velocity inside of that pipe. Now, for a lot of literature that you might be seeing, they might still have that as 2.5 feet per second or 0.8 meters per second. This has been a recent change where new research has just shown that, you know what, we actually need those higher velocities to remove that sediment effectively. And then if we want to try to remove biofilms or slimes off of the sides of the pipe, we are going to try to get up to at least 5 feet per second or 1.5 meters per second of velocity inside of the pipe. So overall, we're going to always try to achieve that higher velocity, right? We're going to really target that 5 feet per second. If we can't make it there, well, hopefully we can at least get over that 3 feet per second with our flushing program. And we'll show later on how we're able to measure that. Now, this diagram is just the idea of why we want to do a unidirectional program rather than just regular flushing. So we're trying to show here if we have a loop system and you're going to the fire hydrant in that loop system and you're opening it up and you're measuring the flow out of there and you're getting that 1,200 gallons per minute. And 1,200 gallons per minute, that's a great flushing volume. If we looked at the charts that we're gonna show a little bit later here, that number would say that yes, you're getting really good velocities in your flush. But because we have no control of where the water is, if we actually looked at the flows that we're actually achieving in the pipes, we would see that none of them are even reaching that minimum of that 3 feet per second. So although the total that we're taking out of the hydrant seems quite large, the actual flow through each individual pipe is so low that we're not really doing any type of cleaning of the pipe itself. All we're doing is discharging water. Right? So we want to change this program then. We want to make sure then that the flow that I'm reading coming out of the fire hydrant is the same flow that is in the pipe that I'm trying to clean. So we've got to start taking our flushing program and changing it into a UDF. This can take some time, can take some effort if it's the first time you're going through it. Maybe some of you have an old system that someone else did and you're just looking to upgrade it. But if you're just starting out from scratch, you've got to be willing to spend some time and effort at the desk first and do some planning to make sure that this is going to be effective for us. For most programs, it's always good to have one person assigned to be in charge of the program. They can delegate other tasks down to people, but if there's too many fingers in the pie, obviously sometimes that doesn't see any type of completion because everyone thinks that someone else is responsible for it. So if you have one person, like, okay, this is going to be my program, this is the way we're going to do it. Now, we will cover this again at the end about the unidirectional flushing program. This is always changing. This is something we always call a dynamic document. Just because you make up the program this year and put your stamp on it and go out and do it and it works well, doesn't mean that next year something else doesn't need to be tweaked or changed with the program. Or same for some of you who maybe have an old program and you're looking to update it. Well, just try to start over all the steps and maybe put some fresh eyes on the UDF program that you have, and you can maybe see some good positive changes that you can make to it. So some of the tasks where you might need some additional staffing, or for a lot of you will be whoever's writing the program will be doing this also. You're going to have to write up a procedure for doing this flow flushing program. That's going to include where am I flushing from, what valves am I closing, how is this going to work for us. Someone is going to have to go out and locate and ensure that the valves that we are marking out on the map that we need to close, that we know where those are and that those valves actually operate. We're also going to have to go out and service those flushing points, right? We're going to have to make sure all those points that what we're going to flush from are going to work for us. We're going to look at some data that we can try to collect even before we go out and do the flushing, but also during and after the flushing, that will lead us to tell us how effective our flushing program has been. At the end, every time that you go out and do a flushing program, with the UDF, you're going to have to evaluate it, right? You're going to have to be, hey, while I was out in the field, this didn't work, this was a little bit different than what we had written. So we have to be open to adjusting that flushing plan. And you might make a recommendation for a change, try it the next year, and that doesn't work either. So you've got to, as I said, this has to be a dynamic program. We have to be willing to make changes to it every year. So the first part, like anything, when we're going to get ready to start planning out our unidirectional flushing plan, is we need some good system maps. So we need maps that show the entire system from the water source all the way to the very last user. We need to know what all the sizes of the water mains are. We need to know where all the hydrants and blow-offs are, and we need to know where the valves are. If we have some missing information, well, we need to go out and update those maps first so that we can really start to plan this out. So we don't need everything like all the service lines. As I said, we need where's the source, the entire system all the way to the end, what size water mains we have, the valves, and any hydrants or blow-offs that we're going to use during the flushing program. So we got to gather all that information first, have some sort of print up of that information so that we can start to plan this out at our desk. So when we're looking at our system maps, we're going to want to start our plan from the water source. So from the water treatment plant, or the reservoir that it flows in directly from the water treatment plant. So we're going to use that, and then we're going to try to flush clean, fresh water from there all the way to the end of all the mains in our system. Now we're going to try to make sure that we focus on making sure that the water is flowing in one direction only. So we're going to look at what valves do we need to close to make that happen. Now we're also going to be looking at measuring some flows. So we need to be able to measure the flow that we are discharging out of our flushing point, because there's a math formula that directly relates those flows to the velocity that we are achieving inside of the water pipes. Now, when we're looking at closing valves in the systems, we got to give ourselves some guidelines and rules. So one of the main ones is that when we close a valve in the system, it should not result in any customers being without water for the duration of the flushing. If there is a situation you have in your system where you've gone through it numerous times and you've looked and looked and looked, and you're just like, no, there's just no way I can flush this section of water main in one direction only and not put someone out of water, then we're going to have to look at notifying that customer and making sure that they understand that during the times that we're doing the flushing, they're not going to have water at their location. Once again, though, for the general rule, when we're planning things out, we're going to look at trying to do this so that no one in our system is out of water while we're doing this. The second one is another one there where, yes, people are going to experience some pressure loss while we're doing the flushing, but the system pressure should always remain above 20 psi. The KPA reading has gone off there, but it must stay above 20 psi at all times. And this is for cross connection control purposes, right? If we drop the distribution pressure below 20 psi, we are creating a back siphonage event, and we have a chance then of contaminating our water system. So this one's a pretty critical one for unidirectional flushing programs, especially when you're going through it the first time. Is when we're looking at the plan and we're putting this together, we need to try to give a critical look at the map and try to pick out some spots where, like, you know what, this we might have low pressure here while we do this flushing event. And when we go out and run the program, we're going to make sure then we put pressure gauges out in those spots we looked at, and try to measure that pressure and see how far does it drop when we did this unidirectional flush, and were we able to stay above this 20 psi. I'll give you some examples of one I did some years back, where on the map everything looked good. We did pick out an area we were concerned about the pressure. We went out, we did the flushing program, and we did create a low pressure zone. We actually knocked out a whole section of the water system. The pressure went down to zero. So, we had to stop our flushing program, and then go back and reassess the way we were doing that. So this is also that idea, like, while we're sitting at the desk and we're mapping things out, we want to think about different scenarios, but we can't plan for everything. At some point, we do actually have to go out in the field, run the program, and collect the data. And then, we might find out that, yeah, we thought we are going to get low pressure here, and turns out we did. We need to adjust the plan here. So we need to always be ready to make changes. Valve exercising is also very critical for this. Before we get out and actually do the plan, if we've identified, I'm going to close this valve here, I'm going to close this valve over on this street, I need to go out there and, make sure that I can find that valve, make sure it exists. If it's buried, dig it up, and I need to exercise it, right? I want to make sure that it's going to work when I'm going to do the flushing, right? I don't want to set up all my gear, send out all my notices, be there ready to do this flush, and then realize that, oh, this valve is seized and I can't close it, and therefore I'm not going to be able to achieve this the flushing that I thought I was going to, right? We want to go out and do that first and make sure that everything's going to work for us. Now, when we're also at our desk looking at those initial plans we're going to make, we need to look, are there different pressure zones in my system? If there are, well, then we're going to flush one pressure zone completely and then move to the next pressure zone and flush that one completely. Are there different water sources, right? Do I have, reservoirs at different locations in my water system? And how am I going to isolate those reservoirs so I'm only pulling from one rather than the other one? Or is there some other way where, I can close some valves in the system where one reservoir is feeding the water to the community and the other reservoir I'm using for flushing? Whatever it happens to be in your unique situation, you do need to look at those situations. Now, the other one we're going to look at when we're doing our flushing runs also is we want to break down our system into very small chunks, right? We want to look at how much can I reasonably achieve in one day, right? How many flushing runs? And this might be limited by the size of your community. Maybe I can only get 2 or 3 runs done in a day because I have to go back and forth so often to the valves and to the hydrants that I'm flowing from. It might also be a limit of your water capacity, right? Maybe your reservoir doesn't have enough capacity to do more than 1 flushing run or 2 flushing runs a day. So I need to limit myself that way. Now, the other key rule we're going to look at when we're doing our planning is our flushing runs need to be sequenced so that we're always moving water from clean areas to dirty ones. So we're always, I did a flushing run down a main. I've got clean, fresh water in that main now, and now I'm going to do another flushing run off of that main and draw clean, fresh water again into another dirty section of the system. The next point is also a pretty important one. We want to keep our flushing runs. We like to try to optimize them. We like to do as few flushing runs as possible and achieve the goals that we're trying to achieve. But that doesn't mean that we just go to the very, very far end of our system, close all the valves that it takes to get to that very, very far end, and let it go. We want to try to limit those flushing runs. 500 meters, 600 meters of pipe length, that is what the AWWA recommends again. If you're taking those longer runs, you're not going to be as effective. And this is, again, just, if you're stirring up debris and you're picking it up off the bottom of the pipe or tearing some slime off the side of the pipe, you need to keep that suspended until it gets out of the main. So if you're doing a run that's a kilometer long, well, that debris that you're picking up, it just has so much time then for it to get caught in a elbow, caught in a bend. We just need to carry it for so far to get out of the pipe that it might not be effective for us. So once again, we want to keep those runs reasonably reasonably short. Now, that said, tied into that one also, the last one we have with trying to be efficient or effective with our flushing is when we're looking at the map and we're drawing and we're starting to make out the plan. If there's a way that we can use the same discharge point for multiple runs, we want to try and do that. And once again, this is just a way to be more efficient out in the field where, I've set up all my diffusers, I've set up all my equipment to do this flush. It takes time and effort to take all that stuff off the hydrant or blow off and move to another location and set everything back up again. So if I'm able to do multiple flushing runs from one location, I'm gonna try to do that. And we'll look at some scenarios for this where we can just change some valves in the system and we can change the configuration of the way the water flows to our discharge point, and that will make everything a lot more efficient for us out in the field. So this one just kind of summarizes all those points again. If we have a summary like this sitting next to us while we're at the desk and we're planning this out, we can always refer to it, right? When we draw out, hey, this is going to be my flushing run I'm going to want to do. I can look over to here and then, I can see, do I meet all these general rules, right? I'm going from cleaner main to a dirty main, right? I'm going from a large main to a small main if I've got different main sizes, right? High pressure zones to low pressure zones. My runs are reasonably sized. Now, the last couple of ones there, these are things that we're maybe going to have to do some calculations. We're going to make sure that we time our flushes so that we can do 2 turnovers of water in the pipe. And this is, again, this is a AWWA recommendation. This is how to do effective flushing. And we'll show that calculation coming up here. And then going down to those last two, right, we want to keep that 140 kPa or that 20 psi in the water system at all times. And no one is out of water while we're doing the flushing program. So if we can answer all those questions on the desk while we have planned things out, hopefully when we go out into the field, we can confirm that all those things are correct. Now we also need to look when we're sitting at the desk and looking at the map, we need to highlight areas of concern for us. So, do we have areas that have high water use or are very sensitive for their water consumption, right? So, things like schools, is there a hospital or a care center, any type of commercial user, restaurants, things like that that we need to be aware of in our water system. And for those ones, once again, we got to think up a plan for those ones, right? How are we going to flush by this location without disturbing this location? And for some of those, it might be that you're just going to have to do the flushing on a weekend while the school is closed, or you might have to go in at night. Right, we're going to have to do flushing at 7 o'clock at night because we're going to go by the commercial area or the place where the cafe is. So we're going to go by when they're closed and not disturb them while they're open. For those of you who do have GIS maps of your system, so you have digital maps of your systems, there are a lot of different software programs and maybe even part of your GIS program that you have that do have a unidirectional flushing component to them. And the GIS system will spit out the initial plan for you. Once again, with a GIS system, though, they're only good as the information you put into them. So, they might be able to make a plan for you. Look over that plan, looking at those critical questions that we just covered, right? Is it only going in one direction only? Is there somewhere the plan that this program made where someone's going to be out of water or have a low pressure zone in my system? Right? So we can use this as an initial starting point, but once again, don't take it for gospel that the GIS or the computer program you put all your information in has spit out a perfect unidirectional flushing program for you. Right? You need to look at it with a critical eye also. So when we're looking at doing the initial plan, right, we've got our map, we've got our list of questions. We're going to really just focus on the very basics right away, right? So what valves am I going to operate to do this flush? Where am I going to flush the water from? So where are the hydrants or blow-offs that I'm going to flush from? And then looking at areas then that may or may not have some pressure problems while I'm doing this flush. So we're just going to start with that information. So my initial plan can be very simple, right? You don't need to do anything complex to start with. I do this quite often with operators in their system, and they just use a notepad and start making some notes, right? So they will write something like we have here, right? Okay, well, the first thing I'm going to do, I'm going to close the valve at the corner of Fir and Cedar, and I'm going to flush from hydrant number 2 at the end of Cedar Road. And once again, that's all we need for the initial plan, right? And we can continue on writing out all the different flushing runs to complete the whole system. Now, as you work on your plan, there's different ways we can do this. Quite often the easiest one is you've got your paper copy of your map, is you can just take a highlighter and highlight, okay, on this flushing run, this is the section of water main I'm going to flush. On this flushing run, we're going to go from here to here, and you can highlight that. When you're all done, the whole map should be all highlighted, right? You're like, okay, we've made it. We've made it throughout the entire system. Every main in my system has now been flushed, and I have my list of runs that include the valves that I'm going to close and the hydrants or locations that I'm going to flush from. So we'll look at I don't have I just made up a quick little graphic map to use for this presentation here. But let's say this was my map of my small water system. Right? So I'm going to look at starting to do a unidirectional flushing program here. So I've got my map. I'm just going to start picking away at how am I going to get from water from the water supply all the way to all the very far ends. Now, one of the key things about a UDF is there is no perfect way. There's no correct way to do it. If you hit all the goals, you have done it correctly. And just because one person does it one way and someone else does it a different way as far as the plan and the way that the hydrants they use and the valves they close doesn't make one system better than the other. Once again, all we're trying to do is hit those goals of clean water from the water source to the very far ends, no one out of water, maximizing the velocity. Okay, we have a unidirectional flushing program. So in this case, I decided I'm going to go this way. This is going to be my first run, right? And someone else may have decided, you know what, I want to go and do that loop over onto the far right. I want to do that first instead. Once again, their plan is no different than mine as long as we at the end meet all the same goals. So you can see here, I've decided I'm going to flush out of hydrant number 11. To do that, I'm going to close valve number 9 there. I'm going to close that valve down in this edge of the loop here. Now, I'm going to close that valve because if I don't close that valve, then I have no idea with the water that is coming past hydrant number 2 there, where that water is coming from, right? Is it water that's going all the way around that big loop and coming down there? And therefore, I don't know that the water, how much water I'm getting between valve 1 and valve 8 on my map, right? Because that might be water that's in the loop. So I do need to close off that loop. And in this case, when I look at my run, I can say that, you know what, all the water that I can measure coming out of hydrant number 11, the only way that water can make it to that hydrant is straight down the main, past hydrant number 1, past hydrant number 2, takes the 90 down past valve 16, and runs straight down that main to hydrant number 11. So therefore, the flow that I measure in hydrant number 11 when I do my flush, that is going to be the same flow in that entire section of water main. I can look at that flow. Once again, we'll pop up a chart here shortly. That flow will tell me what the velocity is. And if I can achieve that 5 feet per second, I have a good UDF there, right? I have a good flushing run. So that's why we need to, even on this one here, if I didn't close valve number 9, then the only way pipes that I have that I can confidently say that I've flushed properly is kind of the water main after valve number 8 to the end of 11, right? And then I'm going to have to go back and do some other flush to get that other section of main there between valve number 1 and valve number 8. So once again, by closing that valve on valve number 9, I have the water flowing in one direction only, and I've maximized the amount of or the efficiency of my flush. Now looking at this again, I might say, the water for everyone in this loop, it's going to go past valve number 2 here, and it's going to loop all around and feed all these people. The people on this loop, they're not even going to notice that I'm flushing. Then for my second run, I'm going to move all my gear and I'm going to move it over to hydrant number 9, and I'm going to flush from there. I'm going to leave that valve 9 closed. And really all I'm flushing now is this small little stub end going from valve 17 to hydrant 9. Now, from my previous flush, I have made sure that I have clean, fresh water down the water main along the bottom here. So when I'm calculating out my flushing time, all I need to do is worry about this little section of main between valve 17 and the fire hydrant. And once again, I know we have to jump around a little bit in this presentation, but we'll show you how to do that calculation shortly. So now I can go and start doing the loop here. Right? So I'm going to draw it out. I'm going to decide, in this case here, I'm going to go all the way to hydrant number 6 here. I'm going to go right across the top. And I'm going to close valve number 12. Whoops, sorry, I went backwards there. And I'm going to close valve number 14. Now, in this case here, if we go in this middle line of the loop here between valve 6 and valve 12, it doesn't really matter if I want to close valve number 6 or if I want to close valve number 12. Once again, there's not a one perfect correct answer for doing a unidirectional flushing program, right? At the end of the day, they both are going to achieve the same result. Now, I will say I do put this one up in my presentations purposely, because one of the things that you might want to look at is it is always recommended and seen that you might want to close the valves that are closest to the main that you are flushing. So in this case here, once again, closing valve number 12, it does achieve the results that I want. I might be better off actually closing valve number 6 though. And the reason for this is this is a big long flush of this main across the top of my water system here. As the water is going and going, past valve 1, valve 2, going past valve 4, it's picking up debris, right? It's picking up that, ripping off that biofilm, picking up the debris that is in this water main. And it might be quite dirty already by the time it's going past valve 5 and valve 6 in my system. Now, if there's anyone in there, down here past valve 6, and they are having a shower while I'm doing my flushing, I might be sucking some of that dirty water down that main, and they might get that surge of dirty water in their shower, their toilet, their bathtub, their sink, wherever they're using water. So, if I did have valve 6 closed, that would hopefully prevent that, and they would be getting clean water coming around on their normal flow around the back side of that loop. But that's one of these ones that we're going to have to maybe experience that out in the field and adjust the plan later, right? So we need to be open to these changes. But I've written out another flushing run. Now this was the reason that we had valve 12 closed here. Is the next flushing run is we're going to switch valve 7 and valve 14. We're going to leave all our equipment up at hydrant number 6. And now we're going to flush down that middle main of the loop. And now in this case here, we've got the valves, so we didn't have to go back and change valve 12, right? So this is one of the things, again, trying to show this idea of, if we can minimize valves we're having to open and close and moving our flushing equipment, we might be able to make the system more efficient. From there, we've got the main sections done, and we can write up then some other flushing runs and get rid of the little extra parts of the loop, right? So you see moving to this one, we moved all our flushing equipment over to hydrant number 7, we left the same two valves closed, right? And now, once again, no one's out of water. Everyone's got flow of water going into their system, or into their home, and we only have the water moving in one direction here. And now I can go around and do these other sections, right? For this run here, again, there's not having valve 14 closed to do this one. Probably should be open, but there's a run coming up where we wanted that closed again. But once again, we could get flow moving around. It's got to go in a weird way to get out to all the people out by hydrant number 6. So in that case, then, yeah, you might look at this one and be, hey, you know what? This looks good on paper, and yes, it does achieve our goals on paper, but maybe out in the field, this isn't a run that's going to be very effective, and we really should open valve 14 here. So we're not going to run through them. Once again, we just kind of hit all the points, and when we're done, oh, that didn't. Whoops, that one didn't show up for me. Okay, sorry. When we're done, what was supposed to be on this slide was, we had it all highlighted, right? It went to every main. We had the whole thing highlighted. So we've made our plan up, right? So we're ready to move on to the next steps here. So now we get to finally leave our desk and go out into the field. So from here, we're going to take out our plan that we've written out, and we're going to go walk the system, right? So we're going to locate all the valves that we have highlighted for my plan, right? I need to be able to operate this valve, right? Where is it? It's uncovered. Yes, it works. We're going to go look at all the flushing points, right? Once again, on the map, I said, yeah, I want to go use hydrant number 7 here. So I want to go out and take a look at hydrant number 7. I want to look at it very, very critically. I want to be able to see, I'm going to be flushing a large volume of water out of this point. Where's the water going to go, right? Do I have good drainage here? Do I need hoses, discharge hoses to get the water to flow into a ditch or into a drainage spot? Do I need some traffic control? To do this flush, I'm going to have to run hoses across the road to get it the flow across the road. Is there anything else of concern while I am walking around the system and looking at, what I'm going to be doing? And then, I need to make notes of that. And it might be as simple as, make sure that you take a 50-foot length of hose out to hydrant number 7 because you need to flush into the ditch that's across the street. That might be the note that I need to make. Or, I might have to go back to the desk and be like, hey, you know what? The drainage around that flushing point I want to use is terrible, right? This is not going to work for me. Before I'm going to be able to finish the flush of my main, I'm going to have to shut down because I'm going to be flooding out a yard or whatever it happens to be. And I might have to go back and try to make changes to my plan, right? So once again, go out, walk the system, locate all the valves, locate your flushing points, look at them with a critical eye, and try to see, is there something here that I need to adjust my plan for, right? Does this look like it's going to work for me? So after we've done that walkthrough, we can make changes to the flushing plan. So we're going to start adding in more detail into that plan, right? We're going to add in the notes and observations from my walkthrough. We're going to try to make some decisions about the field data that we're going to collect while doing the flushing. We're also going to look at, making some recommendations for how long we're going to flush for each flushing run. And once again, we can add in any comments we want. As we're trying to develop that final plan, we should also make space to make comments while the flushing, because while we're actually doing the flushing, something might be arise that we didn't think about, and therefore we've got to change our plan and make sure that we're adjusted so we've got a good flushing system in place here. At this point, we can start to formalize the plan a little bit more. um, this doesn't, once again, have to be great detail or anything. I just use an Excel sheet to do this. But we want to start adding in more information now, all right, flushing out our plan a little bit. So at this point here, we should add in things like, what section of a main is this flushing run, right? What are we actually flushing? What is the approximate pipe length and the pipe diameter that we are flushing? We can use those values. You can put them into an online pipe calculator, whatever it happens to be, and it will spit you out a pipe volume. From that volume, we can start to calculate, estimate a flushing time. So how long do I need to flush from my point to achieve those two turnovers of water within that pipe? And then I can also start to list the actions that I need whoever is going to do the flushing plan, that I need them to do to complete this flushing run. For these types of actions, the more detail you have here is the better for what you exactly need to happen. And whether that's where you're including in, you must notify this person because they're going to be out of water during this flushing run. We need you to put a pressure gauge here and measure the pressure at this point to make sure that it stays above 20 psi. I want you to close this valve at this corner and specify exactly which valve it is. You should also have, especially for your valves, directions on opening the valves afterwards, right? So unidirectional flushing programs are notorious for leaving valves closed, where everyone gets all excited, watching the debris coming out of the pipe, and they wrap it up, and everyone thinks they did a great job, and they go home, and someone has forgotten to go back and open up the valve at the corner of Cedar and Fir, and it doesn't get discovered till next year when they go back and do the UDF and find that, this valve's, it's in the closed position, right? Someone forgot to open it up last year. So it's good to have a checklist and list all those items out in the checklist. Especially for the valves that you are exercising out in the field. Have some space to write out whatever field data you're going to do. Whatever you're going to collect, we want to be able to write that down and be able to look at that later, and also have some space to write any notes about anything unexpected that occurs while you're doing the flushing program. For the field data, we want to look at things like system pressures. So what was the pressure in the system while you were flushing? What was the water flow? That is a critical piece of information we need, right? How much water were we discharging from our flushing point? And then we can also look at some water quality things. So pH, chlorine residual, turbidity, conductivity, right? If we've got meters for it, let's take them out there in the field and measure those values. And we want to measure those values before we flush and after we have completed flushing, so we can see, hey, yeah, we brought the chlorine residual up, the turbidity came down, the pH is good now. So we want to be able to have some data to show the effectiveness of our flushing program. We also, going to make sure that we have all our equipment, signage, diffusers, pressure gauges. We've got all that before we actually end up going out and running the flushing program now. Diffusers, these are used to reduce the energy of the water that we're discharging from the point. And they also can be combined with pitot gauges to tell us the flow that we are actually discharging from the point. And that is, once again, a critical piece of information for our UDF program. Pressure gauges, we also want pressure gauges to put at different points in the system while we're doing flushing. And once again, we're just trying to identify, are we getting very, very low pressure zones while we're doing this flushing, right? We're closing off valves, we're changing the way water flows through our system normally, and we want to make sure that we are not getting any areas lower than 20 psi in the system. Um, when we're doing those, we want to look at both static and dynamic system pressures. So static pressure, that's when we're not discharging water from the system. So what we would normally say, what is our pressure in the system? And the dynamic pressure, well, that's when I have my flushing point open and we're flowing all the water. Okay, what does the pressure drop to now when I'm discharging the water? And if we're just using manual gauges, well, we've got to go over there and read that pressure while the flushing is going. If we want to be very, very accurate with this, we can use data loggers that we can attach to hydrants, and these will digitally read the pressure constantly. And then we can go back and download the information out of these, and we can look and see, hey, when I did that flush, what was the pressure at this zone or this section of the water system. So, and these can also be purchased, wherever you get your normal water supplies from, EMCO, Corix, or Conix, or Andrew Sherritt. They can supply you with a data logger for pressure. And when you download them, I know it's a little bit fuzzy, but this is more what you get is you get an instantaneous pressure of your system. So you can see what it is at all time, and you don't need to have someone standing there writing down pressures constantly. Right? You've got the instrument to do that for you. Now for the flow, we need to be able to measure the flow coming out of our discharge point. We can use a pitot gauge, whether they're a standalone one where you're going to stand next to the hydrant as it's discharging water and get yourself all wet, or you're going to use one that is attached to a diffuser, and it's going to read that flow all the time while you are discharging the water. This is the critical instrument that we need to do a UDF, and it is because of the equation that relates flow to velocity. We don't need to know how to do this equation. There's charts for it. You can, once again, Google it. There's an app for doing this where you can just put in your information and it will spit the value out for you. But like I said, when we're looking at this chart, then, if we look at the second line, the 150 millimeter pipe size, so a 6-inch pipe, what do I need to achieve to get those velocities, inside of the pipe? Well, we can look at the first part. If I want to get that 3 feet per second or that 0.91 meters per second, whether you're doing this in metric or imperial, well, I need to discharge at least 1,000 liters per minute or 264 gallons per minute out of my flushing point. And if I can do that, I'm getting my 3 feet per second, right? I'm achieving that first level of scouring velocity. Now, if I want to get up to the higher one, well, then obviously I need to discharge some more water. So with that 6-inch main, I need to be able to measure that I'm doing at least 1,680 liters per minute or 440 gallons per minute out of my discharge point to achieve that higher scouring velocity. Now those flows, those are not hard to achieve for most systems. 440 gallons per minute is a pretty easy flow to achieve out of a 2.5-inch port out of a fire hydrant if you have a reasonable amount of pressure in your system. Right, you've got 50, 60 psi static, and it does not drop greatly when you open up the fire hydrant, you're going to achieve these flows quite easily. But again, make sure you have some sort of pedo to measure that, right? So you can make sure and confirm that yes, this is what my UDF, I'm achieving the goals that I'm trying for. Now, the other thing we can do if we are able to measure the flow that we're coming out of our discharge point is we're able to calculate how long do I have to let this flush for to get my two pipe volumes. So the formula is this one here. It's just time equals volume divided by flow. Once again, you can just plug this into apps. Do a Google search for flushing time, and you should be able to find something to be able to spit it in here. You can calculate it yourself if you're adept at doing math problems. Now, when we look at this, um, we can make an estimate when we're sitting at our desk, right? So you're like, well, I don't know how much flow I'm going to get out of my fire hydrant because I've never measured it. So how do I know how long to let it flush for? Well, we can, and sitting at our desk, we can make a quick estimate, and then we can adjust that when we actually get some data, and we can do this a little bit more accurately. But just to give you some ideas then of times that we're looking at here, um, if we've got a 6-inch main, right? I want to get up to that 5 feet per second scouring velocity. So from that chart I just had up, the chart says I need to get 1,680 liters per minute, or 440 gallons per minute in imperial. That's the flow that I need to achieve. So I'm going to make the estimate and say that, you know what, that's going to be my flow that I'm going to get out of my hydrant, because I know that's very easy to achieve out of a 2.5-inch port. So I put in my flushing run, and my flushing run is going to be 100 meters long of that 150 millimeter pipe. I put that into my calculator, online calculator, and it tells me, well, the volume of that pipe is going to be 1,767 liters, or 482 gallons. So I can look at that right away and see, like, hey, that's roughly about a minute, right? That I can discharge that whole volume. And so I got to remember, though, I need to do that twice. So from here, I can say, you know what, I'm going to, at this flushing point, I'm going to have to run it for a minimum of 2 minutes. Now, when I'm out in the field the first time and I'm measuring the flow, I can go back and adjust this and be like, you know what, my estimate was a little bit wrong. I get more flow, I get less flow, and I can adjust things for the next time going through the UDF, right? But we can use this kind of basis of about 440 gallons per minute as our estimate for the first time we're going through. Once again, before we go do the actual flushing, we got to do some public notification, let everyone know what you're doing, because you are going to be stirring up a lot of debris in the main, and if someone's having a shower right on the run that you are flushing, they're going to get dirty water into their service line. So we want to let people know, hey, try not to use water between these hours, and if you do, this is what might occur. Right? You might see low pressure, you might see dirty water, all those things we normally put out for flushing programs, we're going to put out for a UDF also. So now, we're actually out in the field doing the work. We want to measure the water quality. So we want whatever we have decided, and we've got instruments for pH, chlorine, turbidity. We want to take those measurements before we start flushing. And then we also want to take them after we're finished the flushing. So, we want to start taking those after we've got that minimum flushing time has been achieved. Sorry, back to there. So that's the post one here, right? Once again, after we're done, do the same tests. If you don't have a turbidity meter, well, then use a glass jar, use a white bucket, and try to get make sure that the water is nice and clear. You can't see any debris in it after you have finished your flushing. Hopefully, though, you can your water system, you're able to invest and get a handheld turbidity meter that you can take out into the field, because this is a really big, other than chlorine residuals, this is the really big thing that we're looking at, is what was the turbidity in the system after I finished flushing. And remember, we wanted that turbidity to end up less than 1. If you are flushing and you're flushing for a prolonged period of time and that turbidity is not getting down to 1, it is okay to shut down your flushing if you're below 5 and allow the debris then to settle back down into the pipe. So you're going to want to shut your flushing off, but then you're going to want to be able to measure the turbidity, at a service line, or with the flow going very, very low through your flushing point, and just determine, yes, I didn't get down to 1, I'm at 4.5, but every minute it's going down in the right direction. And this is, especially maybe if it's the first time you're doing a UDF on a system and there's so much debris in the system that you're just not going to be able to get it all out in one go. But you're going to be stirring it all up. When we shut the flush down, well, that stuff can settle out into the bottom of the pipe again, and we can let our reservoir levels build up, let people go back to having their showers, and we'll get that debris next time, right? So we might have to take multiple attempts at getting everything out of the system. Um, Chlorine residuals, right? Again, we should see those chlorine residuals come up after we finish the flushing program. So that's we want to measure those pre and post flushing, record those values. Um, it is also a recommendation that before you start your flushing, you might want to increase the chlorine dosage that you have going into the system. Right? This does a couple of things for you. Um, the first one it does is it makes something that's very easy for you to measure out in the field. Right? If your chlorine residual in your water system is normally zero point 0.3, well, if you increase the dosage up to 0.7, right, that's going to be very, very noticeable to you when you're sitting there measuring it and be like, yeah, I got clean, fresh water, right? I've got that 0.7 here out at my flushing point, right? It'll be easy to measure. The other thing is when we're doing flushing, we're going to be disturbing debris in the water mains. And when we disturb that debris, we might increase the chlorine demand. So if we've already increased the chlorine dosage, we already have that protection in place for that organic matter that we might be disturbing inside of the water mains. So we've got two advantages there by increasing that dosage a little bit before we start the flushing program. Now, after we're finished flushing, we can turn the dosage all back, and it hopefully should only take a short period of time, a couple of days, whatever it happens to be, for those chlorine residuals to fall back to normal levels that you normally have in your system. So after we've gone, we did our initial plan at our desk. We got all our equipment together. We went out into the field. We ran the program that we developed. We need to do a post flushing assessment. So we need to look at the data. We need to look at the notes we made, and we need to start making adjustments to our plan. What worked well? What didn't work well? Hey, next time let's close this valve instead of this valve, and maybe this will work a little bit better. Whatever it happens to be. Right now, we can make some adjustments, and the plan will be a little bit better for next year. and a little bit better for the year after. So this is a key one, is my last point there, right? You know, when you're the plan that you made out on the desk, it might not work out in the field, right? So you've got to be willing to try new things, and you know you've got to be willing to possibly make some mistakes out there, right? Like, yeah, you know, this worked great on paper, and when I gave my example at the beginning of one I did a few years ago, where our plan looked great on paper. We went out in the field, we executed the plan, everything looked like it was going great. And then all of a sudden, we are like, oh, you know, we did not expect this. We did not expect that the pressure would drop so drastically in this one section of the water system, right? So, you know, we made a mistake, and you know, we've got to go back now and change that plan. Uh, the other thing, if you do have any GIS systems, you can put the data that you actually collect out in the field into those, and we can start maybe doing some modeling. I'm not going to worry about that one too much here. We want to get to is this here, and this is that idea again that this is a dynamic program, right? You've got to go through this every year. Every time you pull the program off of the shelf and be like, you know what, it's flushing time. We want to go through. We want to look at the plan, get all our equipment together, send out notification. We conduct the program. We collect all our data, we assess our data, and we start over. Okay, no, what's the plan for next time now, right? Is there any adjustments that we need to do? And this just keeps going around and around and around. And hopefully this will be you out in the field, um, flushing away with your UDF that you have planned out perfectly.
Crazy. Oh my God. Take a drink. Oh, I got that on film too. It's going on Twitter tonight.
There you go. Well, I know I had to try to get through all that very quickly. As I think they posted, the slides will be posted on the website, so you can go back and look at the information that we went through very quickly there, and you know, hopefully some of it makes sense for you. And good luck out in the field with your UDF programs. But with that, we'll take some questions here.
Yeah, great. Thank you, Scott. As Scott said, we're going to take some questions now. The first one I have here is Priscilla asks, regarding the flow in the pipe, does pressure affect it?
Yes, so pressure does affect the flow. You know, obviously, you know, if you've got higher pressure zones in your system, you're going to get more flow when you open up that fire hydrant, and those values are going to be higher for you. Yeah, and if you got a really low pressure zone, you might not get to those minimum velocities that we want. So yeah, definitely has an effect.
Great, thanks. Next question. Michael asks, am I wrong in flushing H2 and then H10? I'm assuming these are in your diagrams. Following H9 and then last H11, top down. This is regarding flushing example 3, I believe.
Yeah. So, Mike, no, and I'll go back to it here. No, if you wanted to do something different, and that this would say there's no gold star. This is 100% correct with the UDF, right? Really, you know, if you achieve all those goals of water flowing in one direction only, no one's out of water, you didn't go below 20 psi in your system, then your UDF program gets a gold star. And that's where, again, everyone, when you give them a map and ask them to write a UDF program, they will do it slightly different. Right? But that's also where you need to take that, whatever you wrote up, take it out in the field, do it, and once again, if you are able, after answer all those questions and your answer yes, I got flow in one direction only, I achieved my minimum scouring velocity, no one was out of water, no one got to water less than 20 psi, perfect, right? You have a perfect UDF program.
Awesome. Next question. Jennifer asks, can Scott provide a copy of his template for record keeping for each UDF run?
Yes, not a
Just
problem. I will
one
send that
paper.
in. I will send in a blank copy of it.
Excellent. Thank you. And Jason asks, is there a chart for smaller diameter pipes?
Yes. So that's another one. I would probably just Google it, but that's another one. I think I have the AWWA chart that goes right down to 2-inch lines, and that one should be another one I can send and you can put on the website.
Perfect. Thank you. Next question. Steve asks, hi, Scott. When reviewing your drawings before you flush, how do you identify a potential low pressure zone in your system?
Good question. So you want to look at, now let's I don't know if let's go back to here, let's go to flushing run number 1 here, right? So what you're going to want to look at in this case here with flushing run number 1 is I'm going to be flushing from hydrant number 11. I'm going to be creating a low pressure zone there. The water is all going to be rushing, trying to get to hydrant number 11. So you want to look at things. So this one here, this little line that's going out to hydrant number 9, the water is not going to want to go down that line, right? So that might be where an area where, yeah, I'm going to want to put a pressure gauge on hydrant number 9 and measure that pressure. So you kind of just have to see and kind of visualize where the water is rushing to, and then it is something that maybe with some experience you'll get a better eye for looking at it on the map. The thing I would recommend for you is, especially the first time through, taking pressures at more locations is better than not taking pressures. And once again, you can try to see how some of the hydraulics are going. But yeah, if you've got zones where the water seems to be rushing by, like this one here, that's something that might get flagged, and I want to take a look at. The also, for any time when the water is having, like, I think, sorry, um, I'm gonna get which flushing run I'm trying to look at. Um, Sorry, I know I'm jumping around here. But if you look at your map and it looks like the water has to take a very circuitous route to get somewhere, that's also one you're going to look at. The other thing I don't have on my map, though, is I don't have elevations. So again, if you're flushing, look at the elevation change also, and pay attention to those high zones in your system, especially if you're flushing down at a low point in your system. The water is not going to want to go up into that high pressure zone or that high elevation in your system. So you're going to want to monitor those areas. Or kind of a long-winded question, but hopefully an answer was in there somewhere.
Okay, our next question. Matthew asks, is there a calculation or a rough way of estimating the settling in the water system based on initial turbidity readings? And basically, can you use that to kind of time when you should be flushing?
No, not that I am aware of. I'm sure someone at MIT is working on that, but no, not that I know of. Just got to keep going and keep measuring turbidity.
Okay, I don't see any more questions here. Oh, there another one came up just like that. Neil asks, does biofilm develop in conventionally chlorinated systems?
So biofilm development, there's a lot of things that go into how that develops into the piping system, depending on the raw water quality or treated water quality, what type of uh, makeup that is, what type of pipe you have in your system. So even though you have a good chlorine residual, you can end up with pockets or areas in the pipe where biofilm can still form. So there's just it's a little bit too complex to give a simple answer to, just because the way biofilm forms is different in every system.
All right, thank you. Kim asks, with drought precautions in place, are there changes to the number of flushes conducted per year?
Yeah, so that one, really what we're seeing with that one, Kim, is changes in when people are doing flushing. So typically, we would always say, yeah, we're going to go do flushing in the spring. And what I really see out in the field now is places changing, and they're like, you know what, we're going to do flushing in the fall now, while we got heavy rains, and all our reservoirs are full, and we're not having huge water use in our systems. So I'm seeing more people change and doing flushing, in November, or before it starts getting too cold, right? So we're just trying to change the times that we're doing flushing, right? So that we're trying to get those times when we're it's raining lots and we're getting lots of water supply, and we don't have to worry about the use as much.
Excellent. Dion asks, which is better to flush, 2-inch or 5-inch ports?
Well, that one depends on the flow that you need to require. So if you're on a 10-inch water main and you've got to get those high flow values, then you're going to be looking at. I'm just going to get to the chart here. Sorry, I know it's like, oh, there we go. So, once again, if you, let's say we've got a 10-inch main there, and we got to get those very high flows. Well, then you might look at going out of the 4-inch port. And they do make equipment for diffusers and that will go off a 4-inch port. But really, for anything up to, I'd say, an 8-inch pipe, um, just flushing out of a 2.5-inch port should be sufficient for you, depending on your system pressure. So even that one there, an 8-inch, for that 5 foot per second, trying to achieve that 784 gallons per minute. You can do that with a 2.5-inch port if your system has a reasonable amount of pressure in it.
Excellent, excellent. Mike asks, can you recommend dechlorination chemicals that are available and pros and cons of each, and when you should be using them to flush to fish-bearing streams or to a roadside ditch, for example?
Good, Mike. So something we kind of just skipped right over. When I was talking about the flushing, I was so focused on getting the flushing done. We did not talk about the dechlorination. So you should be dechlorinating all times here when you're doing this flushing program. Which chemicals are better? Whether you're using the sodium thiosulfate pucks or the VITC, using the sodium bisulfate. They all have their issues. You kind of gonna have to look into them and make up your decision for your own. Some of them, like the sodium thiosulfate, those ones have problems of being oxygen scavengers. If you want to go to the VIT-C, which doesn't have the oxygen scavenging problem, well, then you're going to have to pay more, right? The cost of that dechlorinator is quite a bit more. So, yeah, you've got to kind of work that out on your individual system.
Now Kirby asks, I take care of a gravity system that has static pressure of 27 psi at the highest point. How would you handle the flushing? The main line is a 4-inch line.
Yeah, so if you've got resonance hooked up at the top there that have that low pressure, you're going to have some issues there. If it was me doing it, I would locate their service lines and shut their service lines off while I was doing the flushing. And that way, I would use that would give me some sense of protection that while I'm doing the flushing, that I'm not going to be siphoning the water out of those homes.
Excellent, thank you. Chris asks, we need to purchase a Pollard flusher or similar, but can't find a Canadian distributor. Any suggestions?
Yeah, so I've been able to order those through MCO. They have brought them in previously, but I do understand that one. You can order directly from Pollard. I don't know if recently they quit shipping up to Canada directly. Um, Unfortunately, yeah, that's a tough one. Like I said, I would talk to your regular parts supplier though, and just ask them if they're able to import that in for you. Like I said, I've used MCO here in Victoria, and they've done that for me previously. But other stuff, I've just had to go down to a PO box across the border and pick it up myself. It's definitely an issue, and I don't have a solution for you.
Matthew asks, what is the minimum flush exchange, i.e., 2 volumes of the system being flushed, based on?
That Good question. I am just going from the AWWA recommendation, and they are the ones that are looking at all the research that the people do into anything related to water. So I don't know the exact study, but somewhere along the lines, someone has put debris in pipe and studied how long it takes to get that debris out of the pipe, and that has been their recommendation.
Mark is asking if maintaining the water service is not feasible during flushing, does draining and refilling the mains during the flushing make any improvements in the process?
No. Um, no, right? So draining them, that's going to be cause some water quality concerns, especially when you're talking to your health authority that you have drained the water mains during the flushing process. So no, you are going to if that's the case, and there's going to be some special cases out there, we're going to have to look at some alternate way to do that flushing for you.
Arthur asks, can we start with hydrant 1 to make sure the incoming water is clean? I believe this is in relation to example 3 again.
Yep. Nope. Not a problem. Perfect way to do it. And
Excellent.
that's usually the first time we are doing something. It's nice to do a nice short little run and make sure that yep, you've got everything's working the way you think it's going to work. Yep. Perfect. Good way to do it.
Bruno asks, how do you check the biofilm reduction? The test would only show the planktonic bacteria.
So, sorry, is that Bruno? Bruno,
Bruno.
you're going to want to do what's called a heterotrophic plate count in those cases. So that is, it's sampled and tested the same way that you're normally doing your coliform testing. This is a more sensitive test, though. It's looking for a different group of bacteria, and that's one of the tests we would look at to try to quantify how much of the biofilm you're reducing inside of your system. It's another one talk to your drinking water officer about, and they can give you a better description of that test.
Brent asks, how do you know how much excess chlorine to add to the distribution system before flushing?
That one you're going to have to use your best guess. So And so that one might be one of those ones where you say, okay, this is what I thought it was going to be. And then we measured it out in the field and there was way more demand by what we stirred up. And we're going to have to adjust this for the next time. So I usually try to recommend that people go up by about 0.5 milligrams per liter above what they normally have in their system as a good starting point. But yeah, you kind of just have to take your best guess and see how it works for you.
All right. Priscilla asks, have you encountered issues with old house lines with lots of sediments, like from manganese and iron? And is there a way to flush the house line?
Yes, so I have experienced this quite a bit, especially with manganese in systems. For flushing the service lines to the homes, the best thing you can do is just open up, every tap that you possibly can on the home and try to flush those out.
Steve would like to know, if you can't get the pressure you need for the flow rates required, what can you do? Can you bring in a pumper truck or?
Yep, Steve, you have one of the exact solutions to what you can do. You can talk to your drinking water officer again, and explain the situation to them. And you might have to do that. You might have to bring in a water truck that is going to backfeed into your system through a hydrant or through a blow off, and give you that extra volume of water and some extra pressure to do that flush. So that's definitely one of the solutions that you can look at.
Matthew asks, can you clarify what 600-meter flushing runs are? 600 meters from what exactly? From the distribution mains?
Yeah, sorry. Great comment. Yeah, that's what I'm talking about is 600 meters of length of pipe underground. So 600 meters up your distribution main. And I know that might be a little bit long for a lot of your systems, but try and keep them a little bit shorter is always better.
Kirby is wondering, because I believe he asked a question before, just concerned about the PSI when flushing reducing to lower than 20 PSI.
Yeah, so once again, when we go below that 20 psi, that's when we start entering that area where we're going to have back siphonage events happening. So that is why we try to make sure we stay above that limit, and not pull that water out of people's service lines of their homes and possibly contaminate our system.
Samuel would like to know, what are your suggestions for achieving the proper velocity in large diameter pipes?
For large diameter mains, well, then you're looking at um, obviously maybe doing flushing from both ports out of a hydrant, possibly doing it out of the 4-inch port of the hydrant. And if you're going really large, well, you might have to open up multiple hydrants and get that flow up.
All right. Chad would like to know, fundamentally, would you recommend that an operator proceed with simply into implementing a UFD program, or is a multi-step approach preferable prior to the implementation? As we know, the systems may not have fully accurate drawings or established valve exercising programs. Would this typically be a multi-year effort incorporating stage implementation and budgeting to address gaps and issues?
Yeah, so I would always recommend like write the whole program out the way you would like to do it. Go do the walk around, get the documentation in place, and then try to do as much of the program as you can, and then note all those things so that you can bring those up to your administration and that be like, hey, we have this program, this is what we'd like to do, but we're missing this piece of equipment, that piece of equipment. When we tried to run it, we ran into this problem. and we need to fix this, and that'll at least give you some backup, but also will give you some timelines, right? Like, hey, we want to do this again next November. We need to get this fixed by then. We need to get this equipment by the next time we run this through. So yeah, I would recommend try and do as much as you can.
All right, questions are slowing down here, and I think we're just about out of time, so I think I'm going to end it here. Scott, I just want to say thank you for your presentation, much appreciated. And I want to thank everyone online for attending today's webinar. Everyone is going to receive a webinar evaluation, and we welcome your feedback. Thoughtful and constructive input plays an important role in helping us enhance the quality of the website and ensures that we continue offering content that is timely, relevant, and responsive to the needs of the small water systems in BC. If you do have any follow-up questions, please email the Online Help Center and we will forward it to Scott for his reply. Just a reminder, go ahead, Scott.
Oh, no, sorry. Go ahead and finish up.
Your CEU certificates will be mailed to you within a day or so. Just give us a little time to get there. And please ensure that you save them, as we are unable to reissue the certificates. And don't forget to sign up for our next webinar, which is coming up on May 19th, where we'll get an introduction to the BC Dam Safety Program. All right. Thank you, everyone, for attending.
Thank you, everyone. Have good flushing.
Thank you.
Bye.